At 7:30, the morning of June 5, 1976, a worker near the base of the brand-new Teton Dam noticed clear water seeping from rock. Clear water leaking from solid rock isn't inherently alarming, but shortly after, the water turned muddy. Mud means the structure is eating itself. Soil is being carried out from somewhere deep inside. By 9:30, the trickle was a discharging torrent, washing out the face of the embankment. Bulldozer crews were sent down to plug the wound with rock, but the erosion ran faster than any machine could fight it. 2 operators had to be dragged to safety on ropes as their machines sank into the widening gap. Time ran out. At 5 minutes to noon, the crest of the dam sagged and collapsed. The entire right bank third of the main wall disintegrated. More than 2 million cubic feet of water per second tore through the breach. It was a flow many times that of Niagara Falls. A wall of sediment-filled water surged down the canyon, spreading across the Snake River Plain. Sweeping through Wilford, Sugar City, and Rexburg, it traveled over 150 miles downstream, causing $400 million in damage. 11 people lost their lives, as a brand-new federal dam, on its very first filling, had destroyed itself and a massive swath of Idaho in a single morning. The immediate question is why the structure collapsed on that specific Saturday morning. But by the time that first clear trickle appeared at 7:30, the dam was already dead. The frantic 4-hour fight on the surface was a desperate battle against a failure that had been running its course for weeks. To figure out how a wall taller than 10 football fields fails from the inside out, investigators had to ignore the surface wreckage and look deep underground, back to the decisions made months earlier. The flood was simply the final, visible stage of a process that had been quietly destroying the structure in total silence. The geographic foundation of the site was hostile. The Teton River had carved its canyon through highly porous, heavily fractured volcanic rock called rhyolite. Water travels through this kind of stone in ways that are extremely difficult to predict. The engineers' defense against this rock was a deep key trench, excavated directly into steep canyon walls as a barrier. To fill this trench and tie the dam to bedrock, they used fine, wind-blown silt called loess. Properly compacted, it's almost impermeable. But loess requires a specific moisture content to bind correctly. In critical parts of the key trench, the silt was compacted on the dry side. It remained stiff, brittle, and full of microscopic voids. Because the soil was too dry, it failed to knit together into a continuous barrier. This one fact set a trap for the rising water. Wedged between rock walls, the silt experienced arching. Gripping the sides through friction, the earth at the bottom wasn't compressed correctly. Rising reservoir water pressed horizontally against this weakened silt, overwhelming its tiny tensile strength and splitting the core from the inside. This triggered internal erosion, also known as piping. Water entering the crack plucked away individual grains of silt and carried them off. As the crack widened, the water accelerated, removing more soil in a runaway loop that bored a tunnel through the body of the dam. This pipe grew in the dark for days, without any visible warning sign reaching the surface. Standard engineering includes a secondary defense against this process, a filter zone of carefully graded sand and gravel placed downstream of the core. If erosion starts, the filter catches the fleeing soil particles. This clogs the tunnel and chokes off the piping process before it can expand. Teton Dam had no such filter protecting its critical zones. Without a filter, the dam relied entirely on the compaction of the silt, the very thing that had been done wrong. After the flood, a panel of the country's most respected geotechnical experts was assembled to conduct an autopsy on the wreckage. They reconstructed the sequence of events grain by grain. Their conclusion matched the hidden physics. The failure was initiated by hydraulic fracturing and internal erosion, just as the stress calculations predicted. But they also criticized the underlying philosophy of the project. The designers had built a system that left no margin for error, with no provision to safely manage the seepage that is inevitable in any large dam. When safety rests entirely on underground measures you cannot verify, the absence of a visible problem doesn't mean you are safe. It only means you haven't yet seen the failure that is already underway. Teton forced an overhaul of federal infrastructure. It led to a national dam safety program. mandating regular inspections and internal instrumentation to monitor the invisible health of these embankments. Because of this failure, engineers now insist on verification and watching the inside of a dam rather than just its face. A leak you can see is frightening, but the disasters that truly kill are the ones that finish their work in total silence, long before the first warning ever reaches the surface.